other people can join us. You gonna get in there, James? This is vocabulary practice. Yeah. Yep, I can agree with that. Not James. I like it. All right, let's go. He's just being funny. Get in there, Leading. There's the link. Oops, the link was way. Let me get the link back here. There you go. So this is to see who the winner is. Natalia, you seem to be way in the top there, but I've played this game, and a lot of times I can get thousands of points in one strike. So it was kind of cool. I went from 8,000 to 20,000 in just one fish that I caught. So. All right, looks like Natalia and James is going to be in the first. Hayden third. Okay, so thank you guys for doing that. I have a what do you call a public service announcement because we're talking about electricity. Okay, we are talking about. I have had friends of mine and even acquaintances from my high school get killed in car accidents, and this is not a do not text message, but this is just hitting power lines. Okay, hitting a pole, a telephone pole, which we call that. Okay, I can send you a little link. You guys hear this okay?
It wasn't a daydream. It wasn't a
Hello? Sorry, my meeting ran late. I should be home in about a half an hour.
I wanted to grab it.
You can hear it all.
Sure,
Right,
I can pick up dinner. What do you want? Hot and spicy. That's what I'm talking about. I will. I love you too.
It's not a don't text and drive thing, but that's what happens here. After this. This might shock you.
Whoa. Oh, man. So that's what an airbag feels like. My car. Great. I should probably get out and see how bad the damage is. Wait. Are those telephone wires or power lines? Either way, they could be hot. No way to be sure. Don't take any chances. Just stay in the car and call 911. Good thing I actually paid attention during that safety meeting. Hi, this is Stephen Stonebanks. I've been in a car accident. I hit a power pole. I'm on Highway 18, somewhere east of the 356th Street exit, a couple of miles. No, I'm okay, but there are power lines on my car. Okay, yeah, I know. I won't move until you tell me that the line is de-energized. Yes, I will stay put. Okay, please hurry. Thank you.
All right, so here's the interesting part about this is that in my high school career, we had this incident where a pole fell on a car in a rainstorm, and the wind pushed the storm over there, and the car was still was under the pole, and wires were dangling, and the kids in the car one by one got out. Okay, what they didn't realize is the car, because of its tires, insulates you from those electric lines. As soon as they got out of the car, they were dead. So there were 5 people in the car, and they died one by one, thinking that they needed to get out of the car. Now, again, at that time, we didn't have cell phones, right? It was before cell phones, so you can do that. But remember, the car insulates you from electrical charges. You get out, you ground yourself, you're a goner. So that's my public service announcement for today. All right. So, but what we're going to be doing today is we're going to be talking about Ohm's law. Okay, Ohm's law is named after Mr. Ohms. Okay, and where are you? Here we are. You also have an exit quiz. So you notice that there's electricity notes. It's a matching thing. So look at your electricity notes and do that at the end of the hour. Okay, so we're going to do a little quick review of series and parallel circuits. But what we want to do is talk about the relationship between volts, current, and resistance. 3 things. Okay, there's a relationship. It's not that they are related to each other, but they are related. So looking back from yesterday, just remember a series circuit was a device that linked everything in a row. So like series, like I got to read, what is it? Chamber of Secrets before I read the Half-Blood Prince. You know, I mean, I got to do those Harry Potter in order. So series is the same way. Everything kind of goes with each other. So you got to do the series. They're in one loop, and you can recognize it because there is one loop. And here we go. We have one loop back and forth from the negative to the positive, right? So, and they are the cheapest things to make, but they're useful. Parallel, okay, parallel. If you have more than one path and they're parallel to each other, you think about it, they're parallel to each other, and the device can be very useful. So thinking about series versus parallel, 3 light bulbs linked together in a series, one blows out. What happens to the other ones? They all go out, right? But in a parallel circuit, light bulb goes out because there is another path. You can still get to those other light bulbs. Okay, it costs, they have more wires in here, so it costs a little bit more to make. All right, so in this particular one, if you're looking at this as a circuit diagram, let's do pole number 1. Pole 1, this is 2. This is A or B. Which of these do you think is the series, one loop? So if you think about this series as one loop, which one is it? Now, how about you guys? Thanks, Natalia, Leiden. Hey, Stephen, good to see you. Rosa, Lucas, Levi, Janelle, James, Jabari, Hayden, Brennan, and Aiden, and Alexis, and AJ. So I've got, how many have I got? About 5 out of 16. So I got a third of the class. I know it's after lunch, and I had the worst lunch. I went to a restaurant, and it's like I'm feeling sick as a dog. So 3 and 3. So people see this. So again, maybe if I can help you with this, this is a battery, right? This is a battery, right? That's what the battery signals. And then how many loops are there? How many loops if I go all the way around to this battery? There's only one. So what does that mean? One loop. There you go. Thank you. Thank you. It means that there is a series. So if this burns out, then it can't get through. The electricity can't get through there because it burns out. It makes it an open circuit. All right. So thank you guys for getting in there. Publish the poll. All right. So let's go on to the next slide here. Right, so studying the circuits. So we use Ohm's law. So remember, voltage is the force that pushes it. Current is the rate of flow. So you're thinking about, and then resistance opposes the circuit, current circuit. So think of it as a water pipe. All right, and voltage is the pressure from the water tower or the pressure from the well pump, right? But the current is how much water you're in the hose, right? So the current is how much water is coming out. So we've got voltage, we got the push, but the amount of current coming through can change, right? So how fast it goes, the rate, and then the resistance is how big the pipe is. So in terms of electricity, the resistance is how many obstacles in its way, right? So like light bulbs and all kinds of other electronic devices become obstacles where they have to go through. Okay, and that's okay. We want those obstacles because we have our cell phones and things like that. So that is cool for us. All right, now here is Ohm's law. It has an equation, and this is the weird one. Volts is equal to current times resistance. Current is I, right? And it's just a straightforward. So basically the equation used here is the very helpful for people that are making electronic circuits so that they can make things work. Like if you want something to work off 12 volts or 3 volts or something like that, then they need to figure these things out by using these equations that come in handy for that. So Ohm's law says a circuit is equal to the current times the resistance, and volt is I times R. If you solve for I, it's voltage divided by resistance. If you solve for resistance, it's volts divided by current. Now, again, here is volts. Remember, volts is pushing the current through, and the ohms is like you're basically setting up with some resistance, and here it's like a pipe, and you can see this little green amp per person is having to squeeze through a smaller hole, so there's a lot of resistance. So let's take a look at how that works here. So resistance is the opposition to flow, and the amount of resistance depends on the material that we're using. So we're using wires, and they're coated with plastic, so those are the insulator, depending on how good they are conductors. Greater resistance in insulators than in conductors, of course. The measurement is in ohms. That's named after, and it's this omega sign. Increased resistance decreases the current if the voltage stays the same. All right, so here is a link. I'm going to show you a video here that I show you. If here is a 9-volt battery hooked up without any resistance. Okay, let me show you this. All right, I got to turn my pen off first. All right, now I can hit the link. Hopefully you guys can hear this. So notice what happens when I connect the wires to a 9-volt battery. I get a flame, which means that there's too much energy flowing through the circuit. So it has no resistance. It keeps going, and you'll eventually melt the wires. It can cause some damage here. So let me cut these wires and put some resistance in here. And this light bulb has 10 ohms of resistance. You can see it slowed the current down. The 9 volts is still the same. It's a pretty bright bulb. This is a series circuit. Only has one path. Let's open this up. Put an extra light bulb in there. Another 10 ohms. Notice current flowing is slower. It's still that single path. And one more. Let's put one more in here. Even so, now we have 30 ohms total resistance or opposition to the flow of electrons. And the light bulbs are dimmer. The current is even slower. Were you guys able to hear that? Gina said she couldn't. I thought we had it set so you could. She couldn't. Anybody else? You might have to come in and come back out. Oh, you can't hear it either. Oh, okay. So that's not good. Let me try this again. Try it one more time. All right. Thanks, Janelle. Okay, so let's try this again. So notice what happens when I connect the wires to a 9-volt battery. You're okay now? I get a flame, which means that there's too much energy flowing through the circuit. So it has no resistance. It keeps going, and you'll eventually melt the wires. Can cause some damage here. So let me cut these wires and put some resistance in here. And this light bulb has 10 ohms of resistance. You can see it slowed the current down. The 9 volts is still the same. So basically what we're trying to say here, is that we can, with this law, Ohm's law, we can make things to work out for ourselves. Okay, we can make things so that you can use a 12-volt battery or a 3-volt battery or 1.5-volt battery and get things to work for you, because we have that relationship between resistance, volts, and current. Or we could make things that burn things up. So like if you took a 9-volt and put a wire on it, most likely it's going to burn up the wire. It gets so hot that it's going to burn you. If you were to do that with a car battery could explode by putting a wire just between the parts. Where people have done that before is when they've tried to jump another car and they put the wires on wrong, and then unfortunately that battery has acid in it, and you want to deal with acid, and that can really hurt you. So you have to be real careful of that. So that is what we're talking about here. So again, that is the whole idea behind Ohm's law. There is a whole course on electronics. There's a whole you can become electronic technician, but again, electricity is something you don't want to play with. You want to make sure that if you are an electrician putting electricity in houses, you want to make sure you're working with somebody. Okay, you're not working by yourself, because I don't know if anybody realizes this or not, but if you were to hold on to electrical wire, you basically get your hands clamp and you can't let go. All right. I remember in a storm, the electrician went outside my house and he had another guy, and he basically had a rope around him. And if he touched the wire and got stuck, because his hands clamped, you can't unopen your hands. He was to pull him down. So that's the big thing. All right. So you got to be really, really careful. All right, so let's look at Ohm's law here. It says, according to Ohm's law, if you increase the resistance, let me write this out here for a second. So before you vote on this one. All right, turn on my pen. So Ohm's law says volts equals current times the resistance. Right. So if you increase the resistance, so let's say this be current is 2 amps times resistance of 6 equals 12. Right. So that says 12 volts is equal to 2 amps times 6 ohms of resistance. If you increase the resistance and the voltage doesn't change, so we're going to leave the voltage the same. If we increase the resistance and let's say we double it, what happens? Let's increase the resistance. Then what number do I have to multiply here? I have to multiply by 1, right? I have to multiply by 1 in order to keep the voltage the same. So let's ask this question. Let's do this poll question. All right, so this is poll number 2, A, B, or C. Okay, does the current, so current is right here, does it increase or decrease? Okay, current is the first number. So remember, I was at 2 amps times 6, all right, and I increased the resistance, kept the voltage the same. What's the current now? It's 1. It's 1 in current. All right, so the current decreased, right? Let me show you what that looks like, okay? Let me show you what that looks like. Tell me if you can still hear this. All right, so I did this in the
So in this FET
FET
demonstration,
online lab.
you'll see that I have a 9-volt battery and I have a light bulb in
Can
my
you hear that okay?
circuit. It's a closed circuit, so you can see the flow of electricity.
Thanks, Kimmy.
It's called the current. The voltage is the pushing force, and the current. Now, the resistance is how much opposition to the flow. So as if I increase the resistance, so let's say I put a different bulb in there and I can increase the resistance, notice what happens to the current. The voltage is staying the same, but as I increase the resistance, look at the current. Is it going up or is it going down?
So the current went down, okay? So the resistance stayed the same, the current went down, right? Because basically, if you think about it from this demonstration here, you think about what's happening, we're kind of clamping down and letting less of the current to go through. We're making it harder for the current to go through. So what we would really need to do is add more voltage in order to get it through that small space. Do you hear me at all, Janelle? You don't hear me at all. Okay. So go out and come back in. Go out and come back in. Okay. It's the only thing I could make a suggestion to. All right, so let's go here. Okay, so again, battery, 9-volt battery. If I wanted to find out what the resistance was, I want to use a 9-volt battery, and I want to I want to know what resistance I have to make in order to. So I'm going to use 3 amps of power, and I want to know what kind of resistors I need in there to use the 9-volt and 3 amps of power. And it would take 9 divided by 3. Now, the nice thing is we're not doing any math this week. It's mostly vocabulary. Okay, so it's all vocabulary. So here, but you'll have a question like this. Okay, so here is the question. So let me show you this. I'll use my math skills to kind of prove it, right? Okay, according to Ohm's law, if the resistance is doubled, the current stays the same, what happens to the voltage? Okay, so voltage, right? Come on, pen, you were supposed to be on for me. No pen, turn on the pen. All right, so Ohm's law, voltage equals current times the resistance. Okay, so now I'm going to take, if the resistance is doubled, so let's go back to 12 volts is equal to 1 times 12, 1 amp of current times 12 resistance, 1 times 12. Everybody agrees with that. If the resistance is doubled, so still keep my current the same, times 24, then my voltage is going to have to go to 24, right? So that's how I can prove that. I can show you the video on that. Just give me a second here. I'll show it to you. Start the poll here. So what is that saying? Okay, poll number 2. No, this is 3. A, B, C, or D? A, B, C. So what did I just say? Is it cut in half? Is it doubled? Does it stay the same? All right, so let me show you this link while you guys are voting. Turn this off. Here's my, turn that off. Here's my link. So here we have a single circuit with a light bulb, 9 volts, 10 ohms of resistance. Current is currently 0.9 amps. So, and this is at 10 ohms. So according to an Ohm's law, if the resistance is double, so we're going to take 10 ohms and make it go to 20 ohms, and we keep the voltage the same, or I should say, if we keep the current the same, what happens to the voltage? So we'll have to do some adjusting here. So here is 20 ohms, and the current is dropped. So we want to get the current to go up. So to do that, we have to add more voltage. So we want to get that to back up to 9.9 amps. So we had to double the voltage. So if the resistance goes up and we want to keep the current the same, we have to double the voltage. So here we have, okay, so let's see how you guys did. All right, so most of you guys have said that when we double it, okay, we double, because it's 1 times 24, it gives me 24. If we double the resistance, okay, so that is, again, the extent of your questions on the test will be about resistance. This is one type question. It does, this is cut in half, doubled, or stays the same, right? You don't have to multiply it out. I'm just trying to prove to you it does work. Either way, you can see that. Okay, so we don't have any power questions on here, but if you wanted to talk about power, power is voltage times current. And when we talk about things that you have at your house, you have a meter on the side of your house, and it tells when you, there's a little circling wheel, and it tells when you're using power or not. When you got all the lights off and the heaters off, it's hardly moving at all. But when you turn the air conditioner on, whoa, lots of power being used, and you get charged for that. Right, so again, voltage is used up by devices in the circuit. So here's a series circuit. 9-volt battery uses 3 volts each. But in a parallel circuit, so that's why these get dim. That's what so because the more light bulbs you put, the dimmer they get. In a parallel circuit, every one of these light bulbs get 9 volts of pushing power, and they stay bright. So you can add as many lights as you like, and they stay bright. Now it'll discharge the battery faster than the series circuit will, but that's the case you have. Now the things that you want to, last thing we're going to talk about, and then we'll let you get to work on your assignments here, circuit breaker, right? So when you've overloaded a circuit in your house, you may know this or not, you plug too many things in, the iron in the coffee pot, or the coffee pot, the toaster, the microwave, and something, and the circuit breaker breaks. How many people have had to go down to the basement and switch the switch? How many people have had to do that? Say yes or no. You're privileged if you don't have to. So, but this is a precaution and area. It's a safety device, right? Limits the amount of current that flows in the circuit. Because you saw when we had no restrictions of flow, never had to do it. Okay. If you see that if we had never have any restrictions of flow, right, then it can burn up the wires really quick. So there's a limiter that will pop off, turn off, so that you had to go in there. So nobody's had to do a circuit breaker at all? No, you guys better find out where it is, because if you plug too many things in, that thing will go off. Okay, so today what you're going to do, all right, is go to here, right? There are your notes in there. To use those for your notes here, you're going to do the 5-3 public chat. Am I in public chat? Yeah, I am. Okay, so you're going to do the 5-3 exit quiz. 5-15 exit quiz. Okay, use the notes above there, just some helpful matching, because I can tell you every one of those words is in the test, right? So matching is going to be important. Keep your notes handy, okay? Also, what I'm going to ask you guys to do is try to get those 2 assignments, 15-1 and 15-2. Use your notes, because it's all vocabulary. Get that done. Wednesday is day 15-1 is due. Thursday 15-2 is due. All right, and I'm going to give you the big blue button here. So if you are struggling to, because we only have, what do we got? 9 days next week, 5 days next week, 4 days the next 9 days, and then we've got 2 days here. We got 11 days left in. So if you need to have big blue button help to pass this class, all right, I have some solutions to pass. Okay, it doesn't give you an A, but it gives you a passing grade. All right, so, and it basically is you're just doing the quizzes. You're just doing the quizzes and the tests, but you have to get a 60%. So just to let you know, that's all it is. You're going to pass, but you're not going to get a grade. You're going to get a passing grade. You're not going to get A, B, that, or a C. Okay, so if you need some help, I'll give you the link, right? Because I don't want you guys to go into credit recovery or summer school. I want you to get a grade so you can pass and go on to, you will go to 10th grade regardless. If you fail this class, it'll just be, high school does that. They put you on to 10th grade, but then you have 9th grade credits you got to finish, right? So, and I do have some people in the class that are 10th grade and 11th grade, so either didn't pass it or whatever. All right, so I'm gonna let you guys go to